So we're going to get started in a few minutes, guys. I'm just going to give people a chance to take their seats, if you will. They're filing in here. I can see the participant number kind of climbing. So I'm going to give it a minute just to make sure folks are seated and ready to go. All right, let's do this. Welcome to today's masterclass. My name is Lisa Richter, and I will be your host today. For those of you who are unfamiliar with CSIA, and I hope there are not too many of you, we are a global nonprofit trade association with over 450 member companies in 35 countries. To highlight just a few of CSIA's many member benefits, the CSIA Best Practices Manual guides control system integration companies in the setup and running of a solid company. Any SI company will benefit from the BPs, but earning the CSIA certification is a confirmation by a third party that you have deployed them correctly. For partner members, CSIA offers an ecosystem to grow their SI programs, understand their customers' pain points, monitor industry trends, and share their thought leadership. A trusted resource of qualified integrators and suppliers, the CSIA Industrial Automation Exchange helps SIs, industry suppliers, and manufacturers connect and do business. For SIs and partners, it provides a platform to support your content and SEO marketing efforts, position your company and C-suite as thought leaders, nurture prospects by providing a credible source of information about your company and its products. Finally, a reminder that in 2021, you will have increased access to knowledge sharing, community building, and networking throughout the year when you join or renew your CSIA membership. CSIA is committed to delivering extremely relevant content to system integrators while providing partner members access to a highly engaged audience. To that end, CSIA will deliver weekly virtual events on a broad range of topics and experiences, all of which are open to sponsorships. For more information about CSIA, membership, virtual events, and sponsorship and advertising opportunities, contact us. So now I'm going to turn it over to today's speakers, Barbara Vasquez and Raman Valley.
Hello, just a moment to share my screen. Hello, everyone. My name is Barbara Vasquez, Automation Sales Engineer at Arstal USA. And I am very happy to have the opportunity to present today to the CSIA members and guests the topic of today, which is one of my favorite topics, actually, intrinsic safety for instrumentation. We have prepared this presentation with the Arstal team, and Ramin and I will be presenting today. So let's hear from him now.
Yes, thanks, Lisa. Thanks, Barbara. Good morning, everybody. My name is Ramin Valley, and automation engineer at Arstal Canada Limited. I've been working in the oil and gas and HAZLOC industry for over 20 years in different levels. Before I joined Stahl Group 4 years ago, I have been working for a couple of DCS and system integrator type companies, and I had to deal with the system architectures like this all the time. Now, understanding the IS solution, what are the IS concepts? What is the isolators, barriers? Why do we need them? How should we document them? How can we do the calculation of the safety and operation values? And finally, the IS cabinet layout was always an additional step for us to design a cabinet, or it was a challenge when we had to consider remote IOs in the classified area. Today, we are going to share some of those knowledge and experiences we had about the IS solutions, and we'll find out why this is now getting very popular in the INC systems. Let's get started.
Okay, so we cannot talk about intrinsic safety without talking about hazardous areas. And we cannot talk about hazardous areas without talking about standards. Ramin and I prepared this presentation for the North America. So for North America, for United States, we have to talk about the NEC. NEC 500 covers the classification of hazardous areas as class divisions. NEC 505 covers the classification of the hazardous area as zones.
Like NEC, we also have our Canadian Electrical Code, so-called as CEC. Historically, we also use the class division concept aligned with the NEC terminology. This concept is still widely used in the legacy projects, and it is allowed to be continued to use for the brownfield project. These codes are now collected in the Annex J18 of the CEC. Apparently, CEC is now more aligned with the international codes, which are based on the zone concept. And in the next few slides, we will see what are the difference or what are the similarities of zone and division system. But in Canada, all these information about zone system are now part of the Canadian Electrical Book Section 18. And we always refer to one of these Annex J18 or Section 18 when we talk about the HAZLOCs. Let's see what is the difference between them.
Okay, so we say that both will classify the hazardous area. So a hazardous area, it's an area that has an explosive atmosphere, right? In this example, we have a tank, which is full of a flammable liquid. And you can see when we're talking about zones, my zone 0 is inside the tank. So we have the liquid, the flammable liquid, and then we have the gases with the oxygen. So that will be the zone 0, right? You always have the presence of the explosive atmosphere. A little bit outside that tank, we have a zone 1, which is normal operations. You will have the presence of explosive atmosphere. And farther away, zone 2 will be abnormal operations. You might have a presence of explosive atmosphere for a short period of time. So when we classify on zones, we have zone 0, zone 1, zone 2 for gas, zone 20, zone 21, zone 22 for dust. The lower the number, the higher the risk. Now, when we are talking about a classification as class division, here we have class 1, which is for gas, and class 2, which is for dust, class 3 for fibers. Division 1, in this case, will be when you normally have a presence of this explosive atmosphere. So here we can see how it takes zone 0 and zone 1. And zone 2 will be abnormal operations, not that often. I like to see it in a graph approach. I think this one explains it a little bit better. So we were saying, right, the lower number, the higher the risk, and the risk is for how often you have the presence of that explosive atmosphere. So if we look at divisions, right, we can see at division 1, you have to cover the highest possible risk. So for a manufacturer like Arstal, if we are making a device that will be installed in a division 1, we need to make sure that device can withstand this highest possible risk, right? Which is this all the way to the top. When we are talking about zones, on zones, remember we have 0, 1, and 2. So now we have 3 zones. We have this zone 0, which is the highest possible risk, right, inside the tank. So then our zone 1 has a lower level of risk. So when we manufacture a device for zone 1, it needs to be able to withstand the highest possible risk of a zone 1, which now it's here. So that's one of the main differentiations when we're talking about, divisions and zones. You can see how the risk changes significantly. I know, Ramin, in Canada, you do have customers that uses divisions and you have customers that uses zones. It's very common to see both of them. What's your experience on that situation?
Some of the friends who used to use the class division concept in the past, and now they are switching to the zone system, they tell me that they have more options to choose a right product when it comes to the zone system. A very typical example of it is HMI. For example, an HMI computer for Class I Div.1 most of the time has to be purged because some of the protection methods are recognized in Div.1, force us to use the purge panels for Class I Div.1. However, when we are switching to the zone concept, most of the time this area is reclassified as Zone 1 and not Zone 0. So we have more options to choose a proper protection method. That means we have more options to use HMI panels without purge requirement. And of course, that means saving a lot during the purge procurement and operation over the time.
And we will talk a little bit more about those protection methods and which ones are recognized where. So that was very interesting to know. So when we are working in a project and our customer, we have the process defined, the customer or the person working on, the team working on that process will let us know the hazardous area, what we have to design the electronics to go there, right? And many times they will say, this area will be a Class I Div.1. Well, we're still missing more information. So the area needs to be classified, also covering the group of gases and the T rating. This is very important information when we want to define the equipment we're going to install in that area. So we have a different group of gases and we have the different T ratings. So the proper classification will be something like American Zone 1 to be T4 or Class I Div.1 Group C T4. So we need the entire part number. And a little bit later, we'll see some examples where that group of gas it's really relevant when we're trying to, again, define the equipment that we need to use. Okay, so now we have our process. We have defined the hazardous area that we're going to be working with, and we're going to install electronics in it, right? Instrumentation, because that's what we're talking here today. Instrumentation like pressure transmitter, temperature sensors, level sensors, solenoids, proximity sensors, right? Beacons, horn, pilot lights. So how do we protect these electronics to make sure we don't get that spark, we don't get that heat that can react with the explosive atmosphere? There are three principles for protecting electronics in hazardous areas. So the first one will be containment. Probably many of you are familiar with it. Containment will be explosion-proof, flame-proof. It's a mechanical protection method that will hold the explosion. So the explosion will happen, your electronic will overheat or will spark, and you do have explosive atmosphere in there. So the explosion will happen, but the enclosure, the mechanical protection, will contain it, will contain the explosion, will make sure it does not propagate into your process, into your plant. Another protection method, or another principle for protection method, will be prevention. Prevention says the spark, the heat, that high energy will not happen in the hazardous area. So you will not have energy enough to react with that explosive atmosphere. So examples of that will be intrinsic safety, non-incendive, non-arcing, increased safety, that type of protection methods. So it does not rely on the enclosure. It relies on all the components. And the last principle will be segregation. So with segregation, we're saying we're going to isolate our electronic from our explosive atmosphere. So when the spark, the heat happens, it cannot react with explosive atmosphere because they are isolated, right? Examples of these will be purge and pressurization, right? You have air, instrument air. So spark comes, and that's it. Oil immersion, encapsulation, hermetically seal. That are some examples of those. Okay, so we do have several protection methods that we just discussed, but not all protection methods can be used in any hazardous area classification. These protection methods are recognized as per the standard. So that's why we say also it's very important to know what standard we are going to be working with. So for example, Class I Div.1, who can we use? Intrinsic safety, explosion proof, purge and pressurization. If we're talking about instrumentation, it's kind of hard to pressurize a proximity sensor, right? So we're mainly talking about intrinsic safety or explosion proof for Division 1. For Division 2, liquid immersion, non-incentive, non-sparking. For Zone 0, we have intrinsic safety. For Zone 1, we have flame proof, increased safety, liquid immersion, powder fill. And for Zone 2, we have limited energy. So you can see all these, and there are more protection methods. These are just examples of some of the protection methods that we typically see. And you can see that it is important to know, again, where you want to install that item. Because you need to make sure that the hazardous rating or the protection method being used, it's recognized for that specific area. Okay, but once that we define and spec out the item for that specific hazardous area, we need to make sure we install it properly, right? Installation matters. So it is very important that we follow the rule for installation and we do it properly. For intrinsic safety, one of the main documents you need to have handy, after the standard, of course, is the control drawing. For North America, every intrinsically safe device needs to have a control drawing. And we need to install it as per the control drawing. And this document, it's one of my favorites because it spells out very clearly what you can do with the instrument and what needs to what you need to follow. So here, I don't know if you are able to see this little font clearly. It says that this device can be installed in a hazardous areas intrinsically safe for Class I Div.1 group C and D. So remember we talk about knowing the group of gases? Yeah, that's why. If your hazardous area is a group B, then you wouldn't be able to use this field device. So again, that's very important to know the entire classification of the hazardous area. So the control drawing will give you, it will spell out exactly where are you allowed to install it. In this case, obviously the barrier that you need to use, how many in this case, and you have all the notes letting you know some of the rules you need to follow for the entity parameters and the values, which we're going to be talking about that in a little bit. Okay, but let's go back to the standard and intrinsic safety. So what is intrinsic safety? The NEC defines it as a type of protection where any spark or thermal effect is incapable of causing ignition of a mixture of flammable or combustible material in the air. An intrinsically safe device will use an associated apparatus. Actually, associated apparatus is the correct name of a barrier. We always call it, I need a barrier, I need an IS barrier. Well, it is an associated apparatus. And this associated apparatus, it's a device that will be part or will energize an intrinsically safe device. So usually it will have two parts, an intrinsically safe circuit and a non-intrinsically safe circuit. So it will merge these two. Okay. So I know what hazardous area I'm going to be working in. I spec out my intrinsically safe field device that is certified by a third-party agency. And typical installation, right? I have a control room where I have my PLC, my DCS, and I have a connection between them. In an ideal world, That's it, right? Everything will work fine, everything will be fine. But in reality is that we don't live in an ideal world. So in the safe area, we could have a surge, we could have a short circuit, we could wire it wrong to AC power instead of DC power, or something like that. So by having this physical layer connecting the hazardous area into the safe area, we have a path forward of high energy, which is risky. So we need to put something like a firewall, something that will analyze what wants to pass into the hazardous area and be like, yes, no, right? And that's exactly what a barrier does. It's a barrier. If we have high energy, it will not let it pass. So that's why we need the intrinsically safe field device and the barrier. So let's say it one more time. An intrinsically safe circuit. It's formed by an intrinsically safe field device, an intrinsically safe barrier, and the wires in between. So intrinsic safety should always be seen as a system protection method. We need the three of them working together to create an intrinsically safe loop. And this intrinsically safe loop will be so safe that if someone breaks the wire, someone do a short circuit, or you have an open circuit, and a spark happens, that spark will never be hot enough to react with the explosive atmosphere. That's why the three of them need to be working together. Something important is we need to do that loop verification. So we need to have, obviously we need to make sure the IS barrier will energize the field device and it will be working, but we need to make sure we create that IS loop. So how do we create it? So let's go in a real life example. We have this pressure transmitter. It is a 4-20 device. On the data sheet, we see that it has operating parameters. It requires at least 10.5 volts and up to 30 volts to work properly. On the same data sheet, we see the entity parameters. The entity parameters are the intrinsic safety data. Here, we can see intrinsically safe apparatus parameters. We have, for example, we're going to use group C, D, E, F, and G. We have 30 volts, 220 milliamps, 1 watt, 6 nanofarad, and 0 microhenries. So this is the safety data, and this is the operating data. So our associated apparatus needs to be able to energize this field device and make it work, right? So it needs to provide at least 10.5 volts to make it work, right? And at least 20 milliamps. But for the safety data, it needs to provide less than the safety data of the field device. So let's check this in a table. I like it better that way. So on my table, every intrinsically safe device will have a set of entity parameters. The entity parameters of the field device is the maximum amount of energy the field device can receive and still be safe. So in this case, this device says I can receive up to 30 volts, up to 225 milliamps, up to 1 watt, and still be safe. It's still not spark, still not overheat. So my barrier has also a set of entity parameters, and it's saying normal or abnormal operations, the barrier will be able to pass up to 27.6 volts, up to 87 milliamps. So we make sure the maximum amount of energy the barrier could pass is less than the energy the field device can handle, right? If I have a table that can hold 100 pounds, I'm not going to put 120 because I'm going to break it, right? So that's what we're trying to do. The barrier will go same or lower. And what about the cable? We say the cable is part of the system, and the cable will store energy. So we do need to make a calculation to make sure that we don't have too much of cable that can store energy that could create that spark hot enough to react. So for that information, we need the capacitance and the inductance. And we need to do the calculation, again, to make sure we don't have too much energy. So cable length is important. Okay, once we do this analysis, we should document it and save it where the loop lives, where the loop exists, and have it there for records, right? Maintenance, troubleshooting, audits, etc. You have that information handy. So again, every intrinsically safe system should have a loop verification. Okay, but exactly, how does the associated apparatus works? Thinner barriers, galvanic isolators, how does that work?
Well, what we can see here is minimum ignition curves determined by some experiments for different gas groups. The one I see here, gas group 2C, is acetylene, which is more or less very equivalent to the class 1 group A as a worst case scenario. For example, this ignition curve shows me that a 30-volt reference voltage, if we are around 150 milliamps, is safe. Basically, we cannot create a spark or heat with this voltage and current, which is capable to create an explosion when we have acetylene. And that means if we consider a safety factor of 50%, 100 milliamps, and if we work only in this area, below 30 volts and below 150 milliamps, we are safe to use the electronics there. And that's what we call as an intrinsically safe. Our associated apparatus, based on the gas group, has to make sure that this voltage and current is limited to that area. Now, how does it work? It's a little bit about the electronics inside the barrier. So a barrier typically has three major components: a fuse, which protects the Zener diode and the other electronics inside the barrier from the short circuit and limits the current at some level. The major component here is a Zener diode. Basically, a Zener diode is a voltage regulator. So it can regulate the voltage. It can limit it to the certain level based on the parameters of the barrier. And if we have a resistor in series with the loop, then we can limit the current as well. So the voltage will be limited by Zener diode. Current will be limited by the resistor in series. It's a very basic concept of the safety barrier. Now, because it's very simple in the circuit, it's very economical solution. It doesn't have too many components. It's very small in dimension. Basically, it has a very small footprint. We can accommodate bunches of them in a cabinet and connect the safe area equipment to the hazardous area, classified area equipment. It's a very simple design, simple installation. Based on the different ratings of the Zener diode and resistors, we can have different types of the solutions for application. It's a very reliable because there are not much components inside the Zener barrier. They don't need any auxiliary power because everything is a passive component and loop power. And of course, it can be certified for Class I Div.2 installation as an associated apparatus to connect the equipment in Class I Div.1 or Zone 0 or Zone 1. So it can be installed in Zone 2, but connect the Zone 0, Zone 1, and Div.1 equipment. There are setbacks here. They need an IS ground connection. Later, I will show which code actually imposes that. For the Zener diodes, you definitely need to have the IS grounding. Safety depends on the low resistance ground because the energy will be discharged through the Zener diode to the ground. So basically, we have to have a ground which can discharge the energy on it to create this protection. And because of this series resistor in the loop, we have a significant voltage drop. So that's another issue with the Zener barriers. We have to make sure that this voltage drop is not too high that we don't get enough energy to power up our field instruments. Now, another solution for that is using the isolator. Basically, isolators use the same concept, but they have a transformer to separate primary from the secondary. And that means we don't need to have a ground, which is connected from safe area to the classified area. The idea is the same, because the energy will be discharged. The energy will not be propagated to the field, but it doesn't have to be to the clean ground. This is an active device because of the transformer, so we need a separate power supply for it. The isolation basically has some other benefits, like the resistor is not there anymore. Basically, the internal resistance of an isolator is very low, so we don't need to worry about the voltage drop across it. And because it has some more electronics inside, it can also change the signal. So we can have like a temperature input connected to the isolator, and then we get a 4 to 20 milliamp signal as an output, or 4 to 20 milliamps change it to the voltage signal. So that's more flexible system because we have more electronics inside it. Now, because of the galvanic isolation, we have some advantage here. The best thing is we don't have to ground field devices to the same ground as the safe area. This connection is not mandatory. It's a simple engineering because you can choose an isolator for your application without doing a lot of calculation. So if we have an analog input, for example, to connect the transmitter to the field, to the safe area PLC, we just use an isolator, which is for analog input application. Digital input, digital outputs, or analog outputs have their own type of the isolator. Because they have more electronics, sometimes they have microcontrollers inside, diagnostic LEDs there. Sometimes you have the more diagnostic features like a relay that we can connect it to the PLC to create an alarm in case of a fault in a loop. They are very reliable products. They have a very good performance against the EMI, electromagnetic interference, or RFI. And they don't need to have external ground connected to it. Installation in Division 2 is permitted, and they can be an associated apparatus to connect Division 1 or Zone 0 equipment to the safe area. Now, because of these features, they are probably a little bit more costly compared to the Zener barriers. They may be large in dimensions because they have a transformer. Few companies like Stahl, they have a technology to create a very small transformer. So basically, we can have isolators which are almost similar footprint as the barrier, but typically the galvanic isolators are large in footprint, and they need an auxiliary power supply. So that might be another challenge if somebody wants to eliminate the power supply in a local panel. They better choose a Zener barrier versus an isolator. Now, system integrators can benefit from other solutions like a DIN rail or pack bus, something like that, to connect the power supply to a group of isolators instead of wiring them one by one for the power supply. Now, we learned that these safety barriers prevent the fault to be propagated to the field area. Now, what happens if we have a safety barrier which is faulty? Let's back to our schematic here. So this schematic shows our typical components in the Zener barrier. We have fuse, which normally, if a fuse becomes faulty, it becomes an open circuit. So we are safe from that aspect. Then we have the resistor, which again, if the resistor becomes faulty, it becomes an open circuit. So we are safe. The barrier is safe. It may not work. The communication or connection to the field may be disconnected, but we are good because we are safe. And A Zener barrier, typically when the Zener barrier becomes faulty or breaks, it becomes an open circuit, becomes a short circuit. So energy will be discharged to the ground if we have a faulty Zener diode. But in a rare situation that a Zener diode becomes open circuit, and then we don't have that path connected to the ground, then we have a second Zener diode. And that means this barrier can have one level of fault tolerated, and the system is still safe. If we have additional Zener diodes, for example, in parallel to the other two Zener diodes, and if two Zener diodes become faulty, then we have a third Zener diode still working and provides that safety features which we need in the field. So that 3 or 2 level of fault tolerance will be indicated in our code as a EXIA or IB or IC. Let's look at the summary of our standard for the intrinsically safe. What we can see in the left is based on the NEC 505 or CEC section 18, talking about the zones. EXIA field devices are recognized and accepted to be installed in zone 0. That means we can, in installation in zone 0 can tolerate 2 levels of fault. EXIB field devices can be installed in zone 1, which means 1 level, 1 fault can be tolerated, and EXIC field devices can be installed in zone 2. And they are all called intrinsically safe, but IA, IB, and IC are the differentiators of the level of the fault. In the NEC 500 or Annex J concept, we just use the IS, intrinsically safe, which is 2 level of the, let's say, fault tolerated and non-incentive for division 2 installation, which is definitely another discussion. How it is presented in the codes? Well, this is a picture of our Zener barrier. May not be the greatest picture, but I just quickly took that picture to show the codes. And let me zoom on the CSA part of it. Yeah, you can see here on the CSA, it's like a soup of the alphabets here, EX, NA, whatever. EX is an indication for the explosion protected method somehow. NA means non-arcing. As Barbara mentioned, this device it can be installed in zone 2 or division 2 because of NA. What we see in the bracket is IA. That means that this device works as an associated apparatus, can be connected to the zone 0, zone 1, or division 1 equipment. And the last, this one, yep. When I zoom on the FM certificate, again, that's one of the certificates we have. This is based on the division. It's more like a descriptive marking here. It mentions that it's a field, it's an associated apparatus suitable for intrinsically safe connections in class 1B, class 1, 2, 3, division 1, group ABC. So basically, it's more descriptive in the NEC 500 word compared to NEC 505. Well, I like that the slide presented by Barbara about the installation matters. That means I never forget that I need to look at the control drawing. And that control drawing is always a best reference for us to start. But in addition to that, there are some other codes that we have to observe when we are using an intrinsically safe loop. 4 of these codes are summarized here: wiring method, grounding, separation of non-IS and IS wiring, and of course, identifying IS circuit. So one of the major advantage of having the intrinsically safe basically is that we can use standard general purpose wiring for which we use for unclassified area, also for classified area. So that's a very good benefit of intrinsically safe signal. We don't need to have extra wiring method like a conduit or sealing or something like that. But at the same time, there are some other considerations when we are moving from one area classification to the other one. For example, we go from zone 0 to zone 1, then we need to have a process sealing. But that's different from our protection method, because intrinsically safe protection doesn't need any sealing for transferring the signal. The other code which is definitely important to be considered is 504.50 or Canadian Electrical Code C22.1-18, proper grounding. So according to the code, we have to have the isolated grounding between the safe area and classified area. That's why we call our isolators an isolator. They are associated apparatus, but we call them isolator because of this transformer inside. Or if we are using a Zener barrier, we have to make sure that the potential between the ground in the field and ground in the safe area is equivalent. Basically, we need a very low resistance type grounding to connect it. And that's part of the protection method by Zener barrier, because we need to discharge the energy to the ground before energy or extra energy being propagated to the field. And that's why a lot of manufacturers, they use a stud bar or some sort of the mechanical connection to the ground to make sure that they guarantee the connection is properly connected to the ground with a very low resistance situation. The other consideration we always have is about the separation from non-IS signal, because we have to make sure that no fault will be connected to the IS, because especially if we have a IS wiring and we connect it to the high voltage or high current, basically we are eliminating that entity parameter calculation. We increase the voltage above the safety level. So that's 5 centimeter or 2 inches. Usually it is based on the authority having jurisdiction, but it's always recommended. Inside the panel, the non-IS and IS signals has to be 5 centimeters far. And when it comes to the wiring, they also have to be 5 centimeters far from each other. So there are some other wiring methods which are referenced in NEC 504.20 or Canadian Electrical Code section 286. This wiring method is basically to segregate or separate the IS cable from non-IS cable. We may be able to use them in the same tray, but those trays has to be mechanically apart. So the interference from the non-IS signal, high-powered signal, should not be affecting the intrinsically safe cable. So there are 2 considerations here. One is the interference, electromagnetic field from the high power, and the other one is protection against the damage, because if you have a damage, high power may be connected or short circuit to the intrinsically safe wire, and that will eliminate the intrinsically safe loop situation. And finally, the NEC 504.80 or Canadian Electrical Code, they have a recommendation for color, and they mandate us to mark the intrinsically safe signals. So every intrinsically safe signal has to be marked as EXI or clearly labeled as intrinsically safe, or if you are using a color code for them, has to be light blue in color. So that's part of the recommendation and mandate imposed by the code. That's why we see a lot of time companies use light blue glands, light blue ducts, light blue wirings. These are the panels, for example, built by Stahl. You can see from the terminals of the I/O card, the ducts, and the cables, the wiring is all in blue colors, and the glands on the bottom. So for the maintenance, it's much easier to look at it as an intrinsically safe signal and do a live maintenance, which is one of the main advantages of having this intrinsically safe. Okay, having said all these things, now we have a better idea why IS is getting more popular in the I&C world.
But let's summarize it. What do we see? It's globally accepted, right? Nowadays, we see how many companies replicate the process in different locations, right? Maybe one of the plants will be in Europe, the other one will be in Canada, the other one will be in Latin America. So they can use intrinsic safety, which will be like the same concept on all these standards. Definitely the installation, what Ramin was mentioning, the fact that we can use non-hazardous wiring techniques in the for the intrinsically safe loop that definitely provide a lot of flexibility and savings for time that takes doing that installation. Because we don't require all those conduits and seals, and maintenance will be more flexible, but also the fact that we can disconnect intrinsically safe loops and still be safe. Remember, the spark is not going to happen. So being able to replace the card, replace the field device for troubleshooting while everything is energized, make the troubleshooting, make the maintenance way faster, which creates savings for operations. Definitely the fact that intrinsic safety, when it's done properly, of course, has that level of tolerance to independent faults and your system is still safe. And also for instrumentation, which is what we are mainly talking about today, instruments require lower amount of energy to work, right? 24 volts, 50 milliamps, something like that. So there is, it's easier for manufacturers to build intrinsically safe instrumentation. So it's, you know, the end users, the system integrators, the OEMs will have more options in the market to find the right instrument required for their process that is rated for Class 1 Div.1, Zone 1 area, Zone 0 area for installation and use. Like Rami and I mentioned, we are R-style engineers. I don't know how familiar the audience is with R-style. R-style designs hazardous area equipment, electrical and automation. Rami and I are part of the automation department, and this is our portfolio. As you can see, R-style products for automation are mainly like interface products. So they exist above the field device level and below the automation level, which will be the controller, the PLC, the DCS. And we do have a lot of intrinsic safety in our portfolio. You can see here we have the Zener barriers that Ramin was talking about. We have the Galvanic isolator barriers. We have Remote IO, which has built-in barriers for intrinsic safety. Foundation field bus intrinsically safe concept, that's FISCO. We have products for that. Ethernet connection, network connections in hazardous areas. We do have products for that. Our HMIs, believe it or not, some of them will have intrinsically safe circuits on their displays, as well as our ground monitoring will use some intrinsic safety circuits to achieve the Class 1 Div.1 installation. So we hope that you have enjoyed this presentation that and I think now, Ramin, we are open for questions. I don't know if you guys saw, we have that question and answer chat.
Yes, do have some good questions over here. One was, what is the difference between flame proof and explosion proof? Let me answer that. Basically, explosion proof is covered under the NEC 500, the NC 1203 standard. The flame proof is under the IEC 6079. There are certain construction specifications and testing requirements which differentiates both of them. And it's a very short platform here to go into more details, but I hope this helps. The concerned audience member, I'm not spelling out names here, can definitely write back to us and we can support them. The second question was, what if the voltage is greater, but the total energy is less? Barbara, you want to answer this? I believe it is for the intrinsic safety parameter. What if the voltage parameter is greater, but total energy is less?
Yes. So it definitely depends how it was certified, right? And that's what we're saying. When you have your intrinsically safe field device, the control drawing is what's going to define what are the rules to use that intrinsically safe field device in the area. So we need to match the entity parameters. So those values need to be, covered by the IS barrier in the right way. We
Perfect.
cannot go above those.
Right. There was one question about customers asking for 2 Zener diode system. I believe this was when Ramin was explaining about fault conditions 1A, 1B, 1C. And the audience colleague has also confirmed that he has the answer to his question. The next one is, do I need to wire the signal in the control system to an intrinsically safe input module card? Ramin, you would like to take it up?
Okay, sure. Barbara mentioned that the associated apparatus has 2 circuits. One is to connect the safe area, and the other one is, which was coded in bracket, to connect it to the classified area. So I assume the answer to question is the circuit which is connected to the safe area is not intrinsically safe. So we can connect it to any field device, any TLC IO card or whatever in the safe area. It's definitely subject to the classified area restrictions. And the other side, which is the bracket part of the code, can be connected to the field device, which is definitely has to be certified as intrinsically safe.
I hope we answered your question, gentlemen. And then there is one more question here, which is, what is the difference between optical and galvanic isolation? Barbara, you can take it up.
No, can you help me with that one?
Ramin.
Sure. Well, like we have some sort of associated apparatus which use the photoelectrics or fiber optic types or optical type isolation. What we see, a transformer isolation, like galvanic isolation, always provides a better level of protection. They can go up to like 1500 volts or 2500 volts, but an optic or fiber optic or photoelectric or phototransistors, they can go only up to 500 volts or 750 volts isolation. So the level of isolation is different. Now, phototransistors are always cheaper. Definitely, they are more smaller. So you can find an associated apparatus based on the phototransistors, but they are smaller in footprint. The level of isolation they provide is not as good as the galvanic isolator type. A lot of time, phototransistors need to have a common ground as well. So again, if I choose a product based on the photoelectric isolation, I always look at the drawing to make sure that the primary and secondary are completely isolated.
One more question, Ramin, I'll direct that to you because you were talking about it earlier. Could you please elaborate 1 Zener diode up to 3 Zener diode with with a diagram, explaining it with a diagram. So maybe Barbara, you can move it back to the slide again. Right, Ramin, all yours.
Sure. Yeah, like in an ideal situation, if we have a faulty Zener diode,
Ramin, let me interrupt. We got some clarification on the question. Could you please elaborate 1 Zener diode up to 3 Zener diodes with AI used with diagram and division wise? So maybe he wants to relate IA, IB, IC, which is a 6079 zone system, to the div system. So just trying to clarify his question.
Sure. If I understand the question correctly, when we have three Zener diodes, or we can tolerate two faults, two independent faults in a field device or in an associated apparatus, then it can be certified as EXIA, and it is suitable for zone 0. Now, if we are talking about NEC 500, which is intrinsically safe for divisions, we don't differentiate between IA or IB. We always should have at least two level of faults to make sure that this intrinsically safe device is certified for division 1. So basically, that's how we are differentiating it. Now, a lot of manufacturers, because they use multiple codes, they have both certificates, like the associated apparatus I presented. We have EXIA. Also, we have the intrinsically safe for division 1 installation certificate on our product.
I hope we answered your question. There's one more coming up. Give me a second. No, that is all. Nothing more right now. So any more questions coming in? Nope, nothing now. All yours, Lisa.
Well,
Oh no, I saw something coming. Sorry,
sorry.
Lisa. Could you also please define diagram of Zener diode? Nazir, can you speak up and clarify what you mean diagram of a Zener diode? With respect to use of EXIA. Barbara, can you go back to those slides?
Hi guys, I just allowed the questioner to turn on his talk. So if you do need to talk to him directly, his mic is on now. So
right, perfect.
I have
Thanks,
that
Lisa.
Yes, of course.
Hello, I'm speaking.
Yes. Yes, Nazir, go ahead.
Yes, sir. I am little bit confused where I can use Zener 1, Zener 2, Zener 3 diodes barrier with respect to EXIA, EXIB, and EXIC. I mean, if I have a one Zener diode based barrier, so in which area I can use either in EXIA or in EXIB or in EXIC.
Raman, take it forward.
Sure. Yeah, basically, these Zener diodes are an internal circuit of the barrier, right? So we are not choosing them. Like, we choose an associated apparatus based on the area classification. Now, if we look at the next slide here, which has the table, I think we should go to the next. Yeah, here. We can see EXIA field device associated apparatus, which are having two levels of fault tolerance. And in a simple diagram, the previous one, it means it has three Zener diodes, can be installed in zone 0. So if we have a zone 0 area, we should use a EXIA associated apparatus or EXIA field devices. If we have IB, which means we have two Zener diodes, that means we are tolerating one fault, then we can use it in zone 1. And EXIC means we have only one Zener diode, so we cannot tolerate much fault. And that's the device or associated apparatus which we can use for zone 2 installation. I hope I answered Nazir's questions.
So we're at the top of the hour. I would suggest that somebody from our stall side put contact info into the chat. So people, if they have questions, can reach you after the event here and get their questions answered. And we can release the rest of the crowd to go on with their day. Sandra, will you please put up my last slide for me? All right, so something's very interesting is happening with the slide there. But basically, there we go. On behalf of CSIA, I would like to thank today's presenters for this informative discussion, and of course, thank you for attending. I'd also like to remind you that a recording will be available for viewing within the next couple of days. Please visit the CSIA website to view past virtual events you may have missed. Finally, be sure to bookmark the CSIA events calendar so you don't miss any upcoming events. This concludes our program for today. Once again, thank you for joining us and have a great day.
Thank you, Lisa. Thank you, everybody.
Thank you.
Bye, everyone.